Welcome to the introduction of basic operation and troubleshooting for the Caterpillar EUI Fuel System. This presentation is a generalized introduction of the features, system operation, and troubleshooting basics for Caterpillar engines using the mechanically actuated, electronically controlled unit injector fuel system. This presentation is not intended to replace the Caterpillar service manual or other service publications. For detailed troubleshooting information, always refer to the latest service publications. The EUI fuel system has been used on most new 10 to 16-liter displacement models of Caterpillar electronic truck and industrial engines introduced since 1988. This fuel system provides very high injection pressures and full authority electronic control for optimal engine performance, fuel economy, and exhaust emissions. Applications include the 3176, 3196, C10, C12, and 3406E engine families. This presentation covers 4 topics: the electronic engine families using EUI, the operation of the EUI fuel system, the operation of the electronic control system, and finally, basic fuel system troubleshooting. Since its introduction in 1988, the EUI fuel system has undergone many design changes to add features and improve performance and reliability. However, the operation and troubleshooting of all EUI systems is very similar. This presentation uses a generalized example of a system with the latest features. The 10-liter displacement 3176 engine was the first Caterpillar engine to use the EUI fuel system. Introduced in 1988, the 3176 was primarily a heavy-duty on-highway truck engine, but was also used in some industrial and marine applications. In 1996, the C10 and C12 were introduced for the on-highway truck market. The same engines were designated the 3176C, 3196 for the industrial and marine markets. The C10, C12, and 3176C, 3196 engines all incorporate several major improvements, including a higher pressure EUI fuel system and improved electronic control system. Caterpillar introduced the first 3406 engine in 1973. The newest version is the 3406E, which is the 14 and 16-liter heavy-duty on-highway engine. Introduced in 1993, the original 3406E was the first 14-liter truck engine to use EUI over the former pump and line system. In 1998, a 16-liter high-horsepower version was added to the 14-liter models of the 3406E truck engine. All 3406E engines use the high-pressure EUI fuel system and advanced electronic control system, similar to the C10 and C12. The EUI fuel system is comprised of 2 subsystems, mechanical and electronic. The mechanical system consists of the low-pressure fuel supply system and EUI injectors. These components produce very high injection pressures of up to 30,000 psi and provide precise control of fuel delivery. This results in improved fuel economy and reduced exhaust emissions. The electronic control system provides full authority electronic control of all engine functions. New features include electronic speed governing, cold startup mode strategy, automatic altitude compensation, variable injection timing, and oil pressure and coolant warnings and derate. These features result in precise engine speed control, unmatched cold starting, low smoke and emissions under all operating conditions, and built-in engine protection. The EUI fuel system and electronics are virtually adjustment-free, Most changes to engine horsepower or performance characteristics are accomplished by installing new electronic software or upgraded mechanical components. To repair the system, first identify and then replace the faulty component. All system components, including the injectors, electronic sensors, harnesses, connectors, and electronic control module, are dealer serviceable. This allows faster repair times and eliminates the need to rely on the fuel system repair shop to make component repairs and adjustments. The operation of the EUI fuel system is quite different from that of previous fuel systems. In order to troubleshoot an EUI system effectively, you must have a basic understanding of how it works. To help you learn the basics of the EUI system, we'll introduce each system component and then show how these components work together. The EUI fuel system consists of 5 major components. Electronic unit injectors produce fuel injection pressures up to 30,000 psi and fire up to 19 times per second at rated speed. The fuel transfer pump supplies the injectors by drawing fuel from the tank and pressurizing it between 60 and 125 psi. The ECM is a powerful computer which controls all major engine functions. Sensors are electronic devices which monitor engine performance parameters such as pressure, temperature, or speed, and supply this information to the ECM by means of a signal voltage. Actuators are electronic devices which use electrical currents from the ECM to change engine performance. An example of an actuator is the injector solenoid. Now that we've introduced the major system components, let's discuss the operation of each component in more detail. We'll start with the mechanical components and then cover the electronic components. Diesel fuel systems use a plunger and barrel to pump high-pressure fuel into the combustion chamber. The cam lobes, push rods, and rocker arms mechanically actuate the injectors. The term EUI is actually an abbreviation for mechanically actuated, electronically controlled unit injector. Major parts of the injector include the tappet, plunger, barrel and body, nozzle assembly, and cartridge valve. The nozzle assembly consists of a nozzle spring, nozzle check, and nozzle tip. The cartridge valve consists of a solenoid, armature, poppet valve, and poppet spring. The injector is mounted in an injector bore in the cylinder head, which has an integral fuel supply passage. On older engines, the injector seated on a brass sleeve, which was swaged into the bottom of the injector bore. The brass sleeve provided a combustion seal and separated the injector from engine coolant in the water jacket. On 3406E engines, an improved stainless steel sleeve is used. This sleeve also separates the injector from engine coolant, but the injector actually does not touch the sleeve. Supply fuel is sealed above the sleeve by an external injector O-ring, and the cavity between the injector and sleeve is empty. The injector nozzle case seats directly on the cylinder head to provide a more positive combustion gas seal. The sleeve is installed with a light press fit and O-rings rather than the mechanical swaging used on brass sleeves. Increased wall thickness on the stainless steel sleeve allows the use of internal threads. These threads make sleeve installation and removal much easier. C10, C12 engines also use a stainless steel sleeve similar to the 3406E. Rather than using O-rings, this sleeve fits in the cylinder head with a light press fit and is sealed using retaining compound on the upper and lower lands. Actuation refers to the type of force used to power the plunger, which pumps the fuel out of the injector. Mechanically actuated fuel systems use a camshaft lobe and rocker arm to provide that force. The rocker arm presses down on the tappet at the top of the injector. The tappet, in turn, presses down on the injector plunger, which pushes fuel from the plunger cavity below the plunger. Fuel displaced from the plunger cavity can flow in two directions. Fuel can flow to the nozzle assembly and to the nozzle tip. However, to flow out of the tip, the injection pressure must reach about 5,000 psi in order to raise the nozzle check against the force of the nozzle spring. The fuel chooses the path of least resistance. It flows around the normally open poppet in the cartridge valve assembly to the fuel supply passage in the cylinder head. When injection is desired, the ECM sends a current to the solenoid on the cartridge valve. The current creates a magnetic field, causing the poppet to close. Fuel flow past the poppet is blocked, and pressure begins to build from the poppet through the plunger cavity to the nozzle check. When the pressure reaches approximately 5,000 psi, the force of the high-pressure fuel overcomes the spring tension holding the nozzle check closed. The check lifts off its seat and fuel flows out of the orifice holes in the nozzle tip. This is the start of injection. The rapid flow of fuel out of the plunger cavity is restricted by the very small orifice holes. Because of this restriction, injection pressure continues to rise very rapidly, even after the nozzle check opens and injection begins. Injection pressures continue to rise until the flow rate out of the orifice holes equals that of the fuel leaving the plunger cavity. Depending on engine speed and fuel delivery, this pressure ranges from 10,000 to 30,000 psi. High injection pressures promote complete combustion and lower exhaust emissions. Pushing the fuel through the orifice holes in the nozzle tip causes the fuel to atomize into droplets in the combustion chamber. Fuel droplets burn from the outside into the center. Large droplets take longer to burn and may not have time to burn completely during a normal combustion cycle. Increasing the pressure of the fuel through the orifice holes creates smaller droplets. In turn, smaller droplets burn more completely. There are 4 stages in the operation of the EUI: pre-injection, injection, spill, and fill. The first stage, pre-injection, starts with the plunger and tappet at the top of their stroke. The plunger cavity is full of fuel, the poppet in the cartridge is open, and the nozzle check is closed. Fuel leaves the plunger cavity when the rocker arm pushes down on the tappet and plunger. Fuel blocked by the closed nozzle check flows past the open poppet to the fuel supply passage in the cylinder head. As long as the solenoid on the cartridge valve is not energized, the poppet remains open, and fuel from the plunger cavity continues flowing into the fuel supply passage. To start injection, the ECM sends a current to the solenoid on the cartridge valve. The solenoid creates a magnetic field which attracts the armature. When the solenoid is energized, the armature lifts the poppet until it contacts the poppet seat. Once the poppet closes, the flow path for the fuel leaving the plunger cavity is blocked. As fuel continues out of the plunger cavity, pressure builds very rapidly. The poppet transfers this pressure through the plunger cavity to the nozzle assembly. When fuel pressure reaches approximately 5,000 psi, the nozzle check lifts off its seat and fuel flows out the tip. This is the start of injection. Injection pressure continues to build very rapidly until the same volume of fuel, pumping out of the plunger cavity, sprays from the tip. Injection occurs as long as the plunger continues to move down and the energized solenoid holds the poppet closed. When it decides that injection should end, the ECM stops current flow to the solenoid. This collapses the magnetic field holding the poppet closed. Spring and flow forces open the poppet almost instantly. High-pressure fuel can now flow around the open poppet and into the fuel supply passage. With fuel injection pressures approaching 30,000 psi, the velocity of the fuel flowing around the poppet into the 100 psi fuel supply passage is very high. This results in a rapid drop in injection pressure. When injection pressure falls to about 3,500 psi, the nozzle check closes and injection stops. This is end of injection. The extremely fast pressure drop from peak injection to end of injection reduces particulate emissions and is an important benefit of EUI. Let's review the operation of the cartridge valve, which is the heart of the EUI injector. In order to perform correctly, this valve must be able to open and close almost instantly, seal injection pressures of 30,000 psi, and prevent leakage of high-pressure fuel during injection. Containing these elevated injection pressures without leakage requires extraordinary manufacturing precision and tolerances. Any high-pressure fuel leaking past the poppet during injection is not delivered into the combustion chamber.